Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the deepest questions you can ask. How will the universe itself die? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the fate of everything. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine for a moment that you are holding a candle in a dark room. The flame flickers, dances a little, and it glows warmly against the stillness. Eventually, though, it burns lower. The wax grows thin, and one day, no matter how carefully you protect it, the flame sputters and fades. That image of a single flame slowly extinguishing is often how scientists describe the destiny of our universe. A place once brilliant with stars and galaxies, eventually growing dimmer, quieter, until there is no warmth left to spread. But of course, this is not the only possible ending. The cosmos is generous with possibilities. It might freeze, it might collapse, it might tear itself apart, or it could even change its very rules in a single invisible instant. And if that sounds unsettling, I promise we will tread gently. Tonight is not about alarm, but about wonder, about exploring, with a soft light, the many ways the universe might take its final bow. The idea of a universe dying may sound dramatic, but in truth, it is an extension of something you already know very well. Everything changes. Everything has a cycle. Your coffee cools if you leave it on the table too long. The bread you bake grows stale. A flower blooms, then wilts. The sun sets at the end of the day, making way for night. The universe itself, vast as it is, plays by these same rhythms. There is no permanent fire burning at its centre, no endless reservoir of youth. Instead, it follows a law called entropy, the slow drift from order to disorder, from possibility to quiet sameness. Think of entropy as what happens when a deck of cards, once neatly arranged, is shuffled so many times that no order can be restored. At some point, the shuffling overwhelms any sense of pattern, and all you are left with is randomness. When scientists talk about the death of the universe, they are often pointing toward this great drift towards stillness. Not a death like a sudden stop, but more like a long exhale. The stars fade. The galaxies fall silent. The heat and energy that once made complexity possible becomes spread so thin that nothing more can happen. It is as though the grand play of creation has run its course and the curtain finally falls, not with a crash, but with a sigh. But before we get too far ahead, it's worth asking, what does it even mean for something as large as the universe to die? After all, you can point to the end of a life, the end of a book, or the end of a season, but how do you measure the end of everything? Perhaps it is best thought of not as a single moment, but as a long path of fading possibilities, a sunset that never ends, stretching over unimaginable spans of time. Physicists have proposed several possible paths that this sunset might take. Some are slow and cold, the so-called heat death, where the universe keeps expanding until stars burn out, matter decays, and only a thin mist of energy remains. Others are fiery and sudden, a big crunch, where expansion reverses and everything collapses back into a hot singular state, or a big rip, where space itself stretches so furiously that galaxies, stars, and even atoms are pulled apart. Then there is the most mysterious possibility of all, the vacuum decay, an invisible bubble expanding at the speed of light, rewriting the very fabric of physics itself. Each of these endings is like a different dream the universe might be having, and we, still awake within it, are left to wonder which dream will play out. It can feel strange to lie in bed and think of such colossal timescales. The universe is already 13.8 billion years old, a number that is hard enough to picture. And yet, when scientists describe its possible futures, they often speak in numbers that dwarf even that age. Trillions of years, quadrillions, exponents so large that the mind simply gives up, like a tired traveller sitting down at the roadside. And maybe that's the right response. You don't need to carry the weight of such numbers. It is enough to know that the universe has its own rhythm, slow beyond imagining, and that it is quietly unfolding around you even now. Tonight, as we drift deeper into this journey, I'll invite you to think of the universe not as a machine ticking down, but as a story being told. Every story has a beginning, a middle, and eventually, an end. But an ending is not only a stop, it is also a completion. Just as the closing bars of a lullaby are not something to fear, but something that helps you rest, the universe's end can be thought of as a final gentle cadence. A rest at the end of a long, beautiful song. And so, with your body settled and your mind beginning to slow, let's set out on this exploration. We'll look at the possibilities, one by one. We'll move slowly through the cold, the heat, the collapse, the tearing, the sudden switch. And along the way, we'll notice how each possibility echoes something familiar from our everyday lives. A candle burning out, a balloon popping, a room growing still. In the end, the cosmos is vast, but the patterns it follows are ones we already know in miniature. That may be the most comforting truth of all, that the universe itself is not so alien, but simply an extension of the same laws that make your coffee cool, your breath fog in the winter, your heart beat, and your dreams drift into the night. If you close your eyes and imagine the word death, you probably see an ending. A last page turned, a door closing, the lights in a room flicked off. But when we speak about the death of the universe, the picture is more elusive. There is no outside observer to declare that it is finished, no book cover to snap shut. The end of everything is not a single instant but a gradual drift, a soft transformation from a cosmos rich with change to one that has no more stories left to tell. In many ways, it is less like a sudden collapse and more like music that slows until the notes fade into silence. Scientists often frame this fate in terms of a quiet but relentless principle called entropy. If that word sounds heavy, think of it instead as the natural tendency of things to spread out, to even themselves to lose their vivid distinctions. A hot cup of tea on a winter morning cools to match the air around it. A neat pile of sand slides and disperses with every gust of wind. Ice cubes melt into water, erasing their sharp edges. Entropy is the universe's way of saying things will not stay tidy forever. And while the law sounds abstract, you encounter it every day, whether you notice or not. When applied to the universe itself, entropy paints a portrait of eventual sameness. Right now, stars are engines of contrast, burning with brightness while the spaces around them remain dark and cold. Galaxies are tapestries of differences, glowing clusters of young stars beside clouds of gas, spirals of dust set against empty voids. Life itself is a dance of imbalance, always drawing energy from food, from sunlight, from the warmth of the earth to keep its delicate order alive. But entropy suggests that these contrasts will not last forever. The sharp lines will blur, the fire will spread too thin, and eventually the universe may settle into a featureless calm, with nothing left to ignite or to distinguish one corner from another. This is why many cosmologists describe the death of the universe as the point where no more meaningful work can be done. Work in this sense doesn't just mean human labour or activity. It means any process that draws from differences, hot against cold, light against dark, high energy against low. When those differences disappear, when everything is spread out evenly like the cream stirred into coffee, then no more engines can run, no stars can shine, no living systems can hold their fragile balance. The universe might still exist, but it will have ceased to tell new stories. It is worth remembering that death here is not necessarily bleak or frightening. It is not destruction in the way we usually imagine it. It is more like the slow cooling of a campfire after a long night, the embers fading until only a faint warmth lingers. The cosmos has been burning brightly for billions of years, scattering galaxies like sparks. One day, those sparks may simply fade into the night. In that sense, the death of the universe is not a violent end, but a return to stillness. Yet, within this broad picture, there are many possible shapes that stillness could take. Some scientists imagine the universe expanding forever, with galaxies drifting so far apart that each one becomes a lonely island in an endless dark sea. Others picture a reversal, the expansion halting, then collapsing inward, galaxies rushing together like waves meeting at a shore, until everything is squeezed back into one final blazing point. Still others consider more exotic endings, space stretching faster and faster until even atoms are torn apart, or a sudden and invisible shift in the very laws of physics, like a stage set collapsing without warning. Each of these fates is a different verse in the same song, a different way of describing the universe's final rest. You might wonder, if the universe can die, does that mean it was ever alive? Of course, in the biological sense, the cosmos is not a creature. It doesn't breathe or think. But in a poetic sense, it does resemble a living thing. It was born in a fiery beginning, it grew and expanded, it created stars and galaxies and planets, and on at least one world, it gave rise to beings who could look up at the sky and ask these very questions. To say the universe can die is simply to acknowledge that even something so vast follows a cycle of change. Another way to think of it is through time itself. Right now, the universe is full of clocks, stars pulsing, planets orbiting, atoms vibrating. These rhythms allow us to mark moments, to distinguish before and after. But in the far future, when entropy has spread energy so thin that nothing changes, the very idea of time begins to lose its meaning. Imagine a day when nothing happens, not a sound, not a shift of light, not a breath. How would you know the day had passed at all? In the ultimate stillness, time itself becomes slippery, as though the hands of the cosmic clock have finally stopped. And yet, while the end seems inevitable on paper, it is important to remember how extraordinary the present still is. The stars above you are not burned out yet. Galaxies still dance in clusters, sometimes colliding in slow-motion fireworks. Life on Earth still flickers, delicate but persistent. Entropy may dictate the eventual silence, but we're living in the music of the middle, an age rich with light and warmth, with rivers flowing downhill, with fires burning brightly, with stories being told. So, when scientists speak of the death of the universe, they are not trying to dampen wonder. Quite the opposite. They are showing how rare and precious this current chapter is. To know that one day all contrast will fade is to recognise how astonishing it is that they exist now. The glow of a star at night, the warmth of tea in your hand, the laughter of a friend, all are temporary arrangements of energy against the backdrop of entropy, all a brief defiance of sameness. Perhaps the death of the universe, then, is not a tragedy to dread but a perspective to cherish. Like looking at the autumn leaves and knowing winter is coming, it sharpens the colours we see today. It reminds us that endings are not the opposite of beauty, but part of what gives beauty its shape. And just as you may fall asleep each night with the quiet comfort that another morning will come, so too can you rest in the knowledge that whatever the universe's final fate, its story has been long, luminous, and full of wonders. Picture yourself walking through a city at night. At first, every window glows, neon signs blink, Street lamps spill golden pools onto the pavement, but as the hours pass, one by one, the lights go out. The shops close, the houses go dark, and the city grows quieter. By dawn, only a few lamps remain, and soon even they flicker away, leaving empty streets under a pale morning sky. This is perhaps the most natural way to imagine the slow fate of our universe. The lights in this case are stars, and the city is the cosmos itself. For a long while it has been bright and busy, but entropy ensures that the lights cannot burn forever. One by one they will fade, until the universe resembles a city abandoned at the edge of time. Scientists call this vision the heat death, or, more poetically, the big freeze. It is the most widely accepted fate of the universe, not because it is comforting, but because the evidence we have today points us in this direction. The expansion of space is not slowing down, as many once thought. It is accelerating. Galaxies are drifting apart, not just moving, but being carried away faster and faster by the swelling of space itself. Imagine dots on the surface of an inflating balloon. At first they are close, but as the balloon grows, every dot recedes from the others. The universe is a balloon without edges, a balloon that does not stop inflating, and its galaxies are those drifting dots. What this means for the far future is a slow unravelling of connection. Right now, galaxies still cluster, bound by gravity into neighbourhoods and superclusters. But as expansion continues, those distant clusters slip beyond our horizon. They do not vanish exactly, but their light will never reach us again. From our vantage point, they fade into invisibility, like ships sailing over an unreachable horizon. Eventually, even the nearest galaxies, those once dancing partners of the Milky Way, will drift so far that their glow disappears into silence. The night sky, once spangled with billions of galaxies, will look strangely empty, with only a few stars left close enough to see. On smaller scales, the fading is just as relentless. Stars like our Sun are engines, fusing hydrogen into helium, balancing the inward pull of gravity with the outward push of radiation. But even the most generous fuel tank runs dry. In time, hydrogen is used up, helium too, and the star's light dims. Some stars end their lives in sudden, brilliant finales, supernovae scattering elements across space. Others end quietly, shrinking into white dwarfs that glow like embers, slowly cooling. Over billions of years, even those embers fade, leaving behind black dwarfs, cold remnants with no light to offer. The grand bonfire of the cosmos becomes, star by star, a pile of cooling ashes. This fading is not sudden. It does not arrive like a storm. It is measured in scales of time so long they almost defy language. 1 billion years, 1 trillion years, and more still. To us living in a brief human span, such durations feel endless. But from the perspective of the universe, they are simply steps on the road. Picture a candle burning, but instead of minutes, it lasts for eons. At the end, it leaves only smoke, only silence, and the memory that it once gave warmth. There is a haunting beauty in this idea. The heat death is not violent. There is no catastrophic explosion, no universal tearing. It is simply the evening of the cosmos stretched out across time. Galaxies dim, stars fall silent, planets grow cold. Energy spreads thinner and thinner until there are no contrasts left. And without contrasts, nothing new can happen. No stars are born, no warmth flows, no light flickers. The universe does not stop existing, but it loses its spark, becoming a vast still sea where nothing stirs. For everyday life, you can imagine this as the moment after a concert ends. The instruments are set down, the echoes fade, and the hall remains. The walls are still there, the stage still stands, but the music is gone. Or imagine winter arriving in a forest. The trees still stand, the landscape remains, but the songs of birds and the hum of insects are silent. Heat death is not an annihilation of the stage, but the end of the play. This fate also reshapes the meaning of distance and connection. Today you can look up and know that the light from Andromeda, our neighbouring galaxy, is reaching your eyes across 2 million years of travel. But in the deep future, that light will no longer come. Expansion stretches the spaces so wide that messages, even those carried at light speed, cannot cross. Imagine trying to call a friend, but the line grows longer and longer until even the sound cannot reach them. The universe becomes not only dark but lonely. Yet within this loneliness lies something oddly gentle. The end, if it comes this way, is not a cataclysm to fear, but a slow settling. Like dust falling after a long day, like a room growing still after laughter, the heat death would be quiet. And though it seems sombre, it also frames our present moment with rare beauty. The stars are shining now, galaxies still shimmer, life itself still burns brightly. Knowing that one day the music will stop only makes the current melody sweeter. And so, when we talk about the long chill, we're not describing a nightmare so much as a distant sleep. A sleep in which the universe, after its long labour of creation, finally rests. We do not know for certain that this will be the ending chosen by the cosmos, but it is the one that the evidence today whispers most strongly. Expansion is speeding up, galaxies are drifting away, entropy is increasing. The city lights of the universe are already dimming, even if we have only just noticed the first windows going dark. If the heat death of the universe can be imagined as the long chill of a city at night, then the fading of stars is the moment when the street lamps themselves wink out one by one, leaving only scattered embers against the dark. To understand this part of the story, it helps to remember that stars are not eternal flames, but delicate balancing acts. Each one exists only because a careful tug of war is being played out between gravity pulling inward and nuclear fire pushing outward. It is this balance that allows a star to shine steadily, like a heart-keeping rhythm for billions of years. But even the most faithful rhythm eventually falters. Consider our own sun. Right now it burns calmly by fusing hydrogen into helium at its core. Gravity presses inward and fusion pushes outward, holding the structure in perfect poise. But hydrogen is a finite supply, and when it is gone, the sun will stumble into a new, less stable stage. It will swell into a red giant, shedding its outer layers before shrinking into a white dwarf. A small, dense ember about the size of Earth, but with the mass of a star. At first, that ember will still glow, faint but steady, like a coal lingering at the edge of a dying fire. But as the trillions of years roll on, even that glow will fade, until what remains is a black dwarf, cold, silent, and nearly invisible against the void. The sun is only one example among billions, but every star shares some version of this destiny. The massive ones burn quickly, living short, dramatic lives that end in supernovae. These explosions scatter elements into space, leaving behind neutron stars or black holes. Smaller stars live much longer, burning their fuel slowly, but even they cannot escape the eventual exhaustion. Over time, galaxies will become graveyards filled with white dwarfs, neutron stars and black holes, each a relic of an earlier age of brightness. It is tempting to think of this as a sad story, but there is also a deep poetry in it. When a supernova scatters its ashes into space, it enriches the cosmos with carbon, oxygen, iron, ingredients for planets, oceans, and even the cells of living creatures. The death of stars is the reason you can hold iron in your blood and calcium in your bones. Every breath you take is shaped by the life and death of distant suns. So when the stars fade at last, it is not only an ending, it is also the completion of a grand cycle of giving, the moment when the universe finally runs out of fuel for its generosity. The scale of this decline is vast beyond measure. The younger stars are still being born today, lighting up nurseries of gas and dust, and this will continue for a long while. But eventually the raw material runs out, galaxies use up their reserves of hydrogen, clouds of gas are consumed, and no new stars take their place. The final generation of stars is born into a cosmos already dimming. Picture the last sparks of a fire glowing against a growing cold. Once they fade, there will be no more. As the eons stretch into trillions of years, the surviving stars continue their slow transformations. Red dwarfs, the longest lived of all, can shine for up to 10 trillion years, far longer than the current age of the universe. But even they cannot resist entropy. One day, their flames too will gutter out, leaving behind cold remnants. When the very last red dwarf breathes its final light, the universe will enter a new chapter, a time when no star shines, no galaxy glitters, and the night sky is dark forever. It is hard to imagine such a sky. For us, the night is always alive with points of light, with a faint haze of the Milky Way stretching across it. Imagine instead looking up and finding only blackness, no guiding stars, no constellations, only the cold hush of infinity. That is what the cosmos will offer in its later chapters, a darkness complete, not because the universe has disappeared, but because it has lost its lanterns. From that point onward, what remains are the remnants, white dwarfs cooling toward black dwarfs, neutron stars sitting like frozen diamonds, black holes patiently waiting in silence, a universe of leftovers, not of beginnings. The silence will not be absolute, for collisions will still occur, rare as they are. A wandering star remnant may pass close to another, igniting a brief flash of energy. But these will be accidents, not patterns, and they will grow rarer as time passes. In the end, silence will win, and in that silence, time itself begins to blur. Our human sense of time is tied to cycles, the beating of a heart, the rising and setting of the sun, the growth of seasons, the burning of stars. In a universe without stars, what rhythm remains? The seconds may still tick, but with nothing to change, nothing to contrast, they lose their meaning. Imagine sitting in a room so still that even the ticking of a clock has stopped, and the air feels endless. That is what the late universe would feel like, time stretched thin, indistinguishable from eternity. If this sounds lonely, there is comfort too. To think of the stars ending is to be reminded that they shine now, that the sky you can see above you is alive with fire, that we live in a brief golden age of cosmic brightness. The night is not empty yet. Galaxies still glow, constellations still guide, and the Milky Way still arcs overhead. Knowing it will one day fade only makes the present glow more precious. The end of stars, then, is not only a scientific prediction. It is a quiet meditation on impermanence. Everything that burns must cool, everything that glitters must dim. And yet, the beauty of the stars is not lessened by their eventual fate, it is heightened. Their brilliance is a reminder of how fragile and fleeting light can be, and how fortunate we are to see it while it lasts. When you think of time, you probably imagine the steady ticking of a clock, or the way the sun slides across the sky, or even the calendar pages that carry you from one month to the next. Time feels like something external, like a river flowing past indifferent to what floats upon it. But in physics, time is not so much a river as it is the measure of change. It is the rhythm of events, the pulse of the universe itself. Without change, without events, time begins to lose its meaning. And in the far future of a universe heading toward heat death, this is precisely what looms. The end not only of stars and galaxies, but of time as something you can truly feel. Think for a moment of a quiet room where nothing stirs. At first you notice the stillness. You notice that the clock on the wall has stopped, or that no sound comes through the window. You can sense the absence of change because you are used to a world filled with it. But what if that silence lasted forever? What if there was no heartbeat, no breath, no flicker of light to remind you of the passing moments? At some point, the very idea of time would slip away, because time only makes sense when something is moving, something is happening. The universe today is alive with clocks, not only the devices we carry in our pockets, but the natural ones scattered everywhere. Stars throb and pulse in cycles that can be measured with exquisite precision. Planets swing around their suns with rhythms we can predict centuries ahead. Even the vibrations of atoms, so tiny and invisible, keep track of seconds with astonishing accuracy. These countless rhythms are what allow us to say confidently that time is passing, but in the late universe, when entropy has drained away the differences that allow cycles to exist, those clocks go quiet. When no events distinguish one moment from another, time becomes a blur, a flat horizon with no markers. Imagine walking along a beach. As long as there are waves lapping at the shore, you can tell that time is moving. Each wave is a new moment. Each retreat of water is a new tick. Now, imagine the ocean has become glass, a mirror without ripples. You keep walking, but without the rhythm of the waves, it is as if you are moving in place. The universe of heat-death would be like that. A vast sea with no waves, only a surface so still that you cannot tell if anything is moving at all. In physics, this is not merely poetic, but fundamental. Entropy is the spread of energy into equilibrium, and when equilibrium is complete, no process can occur. No gradients remain to drive change. Without change, time becomes an abstraction, a mathematical idea with no practical heartbeat. You could say that in the far future, the universe will still have time in a technical sense, but nothing within it will notice. It will be a clock that ticks but never strikes, a calendar that stretches on but never turns a page. This picture raises a curious thought. If nothing happens, can the universe be said to exist in any meaningful way? It may still contain particles, photons, and fragments of energy, but if those particles do not interact, if they simply drift in a uniform fog, then the universe becomes less like a living stage and more like a forgotten painting, hung in a gallery that no one visits. Presence without story, existence without event. It can sound eerie, but there is a kind of peace in this vision too. The universe has been noisy. From the fire of the Big Bang to the fusion of stars, from galaxies colliding to black holes swallowing matter, its history has been dramatic, filled with turbulence and motion. To imagine its end as a quiet settling is to imagine the cosmos finally resting after an unfathomably long performance. Like a violin string that has quivered for eons, finally lying still. We might also reflect on how this reshapes our human experience of time. For us, time feels precious because it is limited. We sense its passage in birthdays and seasons, in the changes of our bodies and our lives. We feel time because we are immersed in change. To contemplate a future where time itself blurs away is to see more clearly what gives time its texture in the present. It is not the ticking of clocks, but the heartbeat of events, your laughter, the taste of dinner, the warmth of sunlight. Time is not simply passing, it is being written in these moments. One of the strangest consequences of the heat-death scenario is that, in the absence of time as we know it, eternity and nothingness begin to resemble each other. An infinite span of unchanging existence feels very much like no existence at all. A day without events feels the same as a year without events, or 1,000,000,000 years without events. The numbers cease to matter, because they describe nothing new. The difference between infinity and zero collapses into the same kind of silence. And yet, within this abstract picture, there is also a reminder of how remarkable our universe is right now. We live in a cosmos that still keeps time. The stars rise and set, atoms vibrate, seasons change, rivers flow. Every moment is marked by countless rhythms, large and small. from galaxies rotating to neurons firing in your brain. The death of time, if it comes, is unimaginably distant, but the awareness of it allows us to appreciate how vivid time still is. So when we ask what time means when nothing happens, the answer is paradoxical. Time, in a sense, will still be there, written into the equations of physics, but it will have no witness, no rhythm, no heartbeat. It will be like music written on a page but never played, a script without actors, a dance with no one to step onto the floor. The universe may last forever in that silent state, but forever will mean nothing at all. Time equals 2 seconds. Imagine standing on a hillside in autumn. The air is cool, the trees are thinning, and leaves that once clung stubbornly to their branches now swirl downward. Some drift gently, carried by breezes. Others are pulled into the slow spiral of a stream, drawn together, circling until they vanish beneath the water. This quiet motion, everything falling back into one place, is not so different from one of the oldest imagined fates of the universe. Scientists call it the Big Crunch, the idea that the expansion of space might not last forever, but instead slow, stop, and reverse until all galaxies, all stars, and all atoms are drawn inward once more. The notion comes from a simple question. What if gravity wins? For billions of years, space has been expanding. Galaxies are moving apart, carried on the tide of cosmic growth. But gravity is persistent, always pulling, always binding. If there were enough matter, enough galaxies, enough dark matter, enough hidden mass, gravity could eventually overcome expansion. The outward push would tire, and the inward tug would gather strength. Just as a ball tossed into the sky slows, pauses, and falls back down, so too could the universe. Once racing outward, hesitate, then fall back inward. If this reversal were to happen, the night sky would begin to change in ways that defy imagination. Instead of galaxies drifting farther into distance, they would begin to approach. At first, slowly, too gradually for any single generation of humans to notice. Then more quickly, as clusters collided more frequently, as distances shortened. What once looked like an endless sea of separation would turn into a crowded storm of motion. Galaxies, those vast island cities of stars, would be drawn together into collisions not over billions of years, but millions, then thousands. Each merger would be a storm of brilliance, new stars born in bursts, black holes colliding with thunderous gravity waves. For a time, the collapsing universe would be filled with light, but that light would not be gentle. As the collapse deepened, temperatures would rise. The background radiation, which today has cooled to a faint microwave glow, would climb again into visible light, then into a furnace of heat. The universe would become brighter, hotter, less hospitable. Space itself would contract, squeezing galaxies, then solar systems, then planets. Imagine every autumn leaf in the forest pulled not just to the ground, but into the same fire, a bonfire consuming everything it gathers. In the final stages of the Big Crunch, matter would be packed closer and closer. Black holes, which normally dominate only their local regions, would themselves be dragged into the gathering collapse. Eventually they too would merge, feeding a final central mass. Temperatures would soar beyond anything stars have ever known, densities rising until the cosmos as a whole resembled the singularity from which it once began. The difference between the beginning, and the end would blur. A universe that began in a Big Bang could end in a reverse event, a bang turned inward, and then, perhaps, something stranger still. Some physicists have wondered if a collapse into such density could trigger a new birth, a bounce, where the death of one universe seeds the expansion of another. The imagery is powerful, a cosmic phoenix, burning into ashes only to rise again, a story of endless cycles where each universe breathes in, then out, forever. It is speculation, of course. We do not know whether such a bounce is possible, or whether collapse would simply end in silence. But the metaphor comforts. It reminds us that even in destruction, nature often folds beginnings into endings. Seeds sprout after fires. Stars are born from the ashes of older stars. Perhaps universes too might rise from the embers of their own demise. For a moment, picture what it would feel like to live within a universe headed for the crunch. The skies would grow more crowded, galaxies closer, collisions more common. The future would not be an empty night but a storm of light. Yet it would be a temporary brilliance, because all that light would converge, drawn tighter and tighter until no space remained to hold it. To the last observers, if such beings could exist in that heat, the cosmos would appear to blaze more brightly than ever, even as it hurtled towards silence. From a human perspective, there is a paradoxical comfort here. Unlike the heat death, where stars wink out one by one into endless darkness, the crunch is an ending of intensity, of fire, of crescendo. It is not a fading lullaby, but a symphony building to its final chord. And within that chord lies the possibility, however speculative, of rebirth. For those who like to imagine circles rather than lines, the crunch is an appealing vision. It makes the universe feel less like a one-time miracle, and more like an eternal rhythm, a heartbeat that slows, stops, and then starts again. Of course, current evidence does not favour this path. Observations tell us that the expansion is not slowing, but accelerating, pushed by something we call dark energy. It is unlikely that gravity will ever pull hard enough to reverse that expansion. And yet, the Big Crunch remains a powerful idea in cosmology, because it echoes a deep intuition humans have always carried, that what begins must one day return, that what rises must eventually fall. So when we think of the crunch, let it not be as a nightmare but as a story where the universe is not lost, only folded back into itself. A story where endings and beginnings blur, where autumn leaves swirl back into the soil to feed another spring. Whether or not the cosmos will truly collapse, the vision reminds us of cycles all around us. The tide comes in, then goes out. Day fades into night, and night back into day. Perhaps the universe itself could follow such a rhythm. And even if it does not, the thought itself is a gentle comfort, a way of holding close the idea that nothing, not even the universe, ends without leaving the possibility of renewal. Imagine stretching a piece of fabric. At first the threads hold. The weave stays tight, though it thins as you pull. Keep tugging though, and eventually small gaps appear. The threads strain, unravel, and one by one they snap, until the cloth is no longer a whole, but a scattering of fibres. This image is at the heart of another possible end for the universe, the Big Rip. Unlike the gradual stillness of heat death or the fiery reversal of the Big Crunch, the Big Rip imagines a cosmos undone by its own restless expansion, a fabric stretched until it can no longer hold together. The idea comes from a peculiar form of dark energy. Dark energy, that mysterious pressure driving galaxies apart, is already strange enough. It fills space uniformly, invisible yet powerful, like an unseen breath pushing everything outward. In our best measurements, it appears constant, unchanging in strength. But some theories suggest that it might not stay steady. If dark energy were to grow stronger over time, its pull on the fabric of space would quicken. Cosmologists describe this extreme form with the quiet but ominous phrase phantom energy. Unlike ordinary matter or even normal dark energy, phantom energy becomes stronger as the universe expands, leading to a runaway effect. Expansion feeds on itself, accelerating without bound. At first, the difference would be subtle. Galaxies already drift apart faster than they once did, so a little extra acceleration might hardly be noticed. But the change would not stop there. Over billions of years, the expansion would become dramatic, turning the universe into something far more unstable. Gravity, which binds galaxies, stars and planets, would struggle against the stretching of space itself. The bonds would not hold forever. The timeline of destruction is almost poetic in its stages. First, galaxy clusters, those great gatherings of hundreds or thousands of galaxies, would come unbound. Their mutual gravity would no longer be enough to keep them together. To any observer within, the night sky would look emptier, as neighbouring galaxies slipped away, torn from the embrace of their group. Then, galaxies themselves would begin to unravel. The Milky Way, with its spirals of billions of stars, would lose its cohesion, its arms unwound like the threads of a fraying cloth. The process would not stop there. As expansion continued to accelerate, even solar systems would be pried apart. Planets that had circled their suns for billions of years would no longer find those orbits stable. Earth, or any surviving world, would drift away from its star as though invisible fingers had cut the string holding it in place. And still the tearing would go on. Stars themselves would be pulled apart, their fusion cores disrupted, their light extinguished not by running out of fuel, but by being literally dismantled. The expansion would grow so fierce that even the atoms making up those stars could not hold together. Electrons and protons, bound by the electromagnetic force, would be ripped from one another. At last, even the quarks within protons might be separated. The smallest threads of the cosmic fabric would be unspooled. To imagine this calmly, picture a sweater unravelling in slow motion. At first it is still recognisable, just looser. Then the threads slide free, the shape collapses, and in the end nothing remains but a pile of yarn. In the Big Rip, the universe itself is that sweater. From the largest clusters down to the smallest particles, all is undone by the acceleration of space. The timing of such an event, if phantom energy exists, would depend on the strength of that strange pressure. Some models predict tens of billions of years before the final rip, others far longer. To us, bound by lifespans of decades, the difference hardly matters. What matters is the idea that the universe is not simply expanding, but may, under the influence of phantom energy, expand itself apart. There is a curious irony here. Dark energy is what currently explains why the cosmos looks set to end in the quiet of heat death. It is the very reason galaxies drift away into silence. Yet if its character is slightly different, if it leans toward the phantom side of possibilities, it would change the ending completely, from stillness to rupture. The same unseen hand could either gently dim the lights or violently tear down the stage. As unsettling as the Big Rip sounds, it can be softened by remembering what it really is, a speculation, a mathematical possibility. Current evidence suggests that dark energy behaves more like a constant, not like phantom energy. We do not see signs of the runaway effect. But even so, the Big Rip remains a fascinating reminder that the cosmos is not bound by our intuitions. Space itself is not a passive backdrop, but an active participant in the story, and its behaviour can shape every possible future. For those who like metaphors, the Big Rip is less like falling asleep and more like a dream suddenly snapping apart. A dream that frays until there is no fabric left to hold the images together. Yet within that unsettling picture lies a certain beauty. The thought that the universe, rather than fading, could end in a final act of motion, a crescendo of expansion that tears even atoms into silence. And so, as with the crunch before it, the rip is both a caution and a reflection. It shows us how delicate the balance of forces truly is, how the very expansion that gives galaxies space to breathe could, in another form, smother them. It also reminds us that endings come in many shapes. Some are quiet, some are fiery, some are sudden. The Big Rip belongs to the last group, but told in soft tones, it becomes less a terror and more a thought experiment. a meditation on how even the strongest bonds can loosen if stretched far enough. Imagine walking across a frozen lake. The surface feels solid, the ice thick beneath your feet. You trust it enough to wander, to look around, to forget for a moment that you are standing on something fragile. But deep within that ice there may be weaknesses, tiny cracks you cannot see. For centuries the lake seems safe, unchanged. And then, without warning, a fracture spreads, rippling faster than you can react. The once solid sheet is no longer steady beneath you. This is one way to imagine another possible fate of the universe, what physicists call vacuum decay. The universe, as we know it, is held together not only by stars and galaxies, but by the invisible rules of physics, the values of fundamental constants, the shape of quantum fields, the stability of space itself. These rules appear solid, like the frozen lake. But what if they are not the final layer of reality? What if the universe we inhabit is balanced on a temporary plateau, a false vacuum, and beneath it lies a truer, deeper ground state? If so, the universe could one day slip, not gently, but in a sudden switch. A change not in objects or galaxies, but in the very stage upon which all of them exist. Physicists describe this with the idea of quantum tunneling. At scales too small to picture directly, particles can sometimes leak through barriers instead of climbing over them. Most of the time this means little fluctuations, tiny shifts too brief to notice. But the same mathematics suggests that a whole universe can behave in a similar way. If our cosmic vacuum is false, if it is not the lowest possible energy state, then there is always a chance, however small, that it could tunnel into the true vacuum. What would that mean? Picture the ice lake again. One moment it holds firm, the next a crack opens, and within seconds it spreads across the entire surface. In vacuum decay, the change would appear as a bubble of true vacuum, forming somewhere in space. The instant it appeared, it would begin expanding at the speed of light, rewriting the laws of physics inside it. Wherever the bubble passed the familiar constants, the charge of the electron, the speed of light, the strengths of forces, could shift. The atoms making up stars, planets, and people would no longer behave as they once did. The universe we know would be gone, replaced by one with different rules. This sounds frightening if taken literally, but there is a strange, soft mercy hidden in it. Because the bubble expands at light speed, there is no warning, no signal rushing ahead to announce its arrival. If such a transition were to happen, it would be instant. There would be no time to fear, no time even to notice. The universe would not collapse in fire or drag itself into silence. It would simply change, in a blink without pain. To us it would feel less like disaster, and more like falling asleep without waking. For now, this remains theoretical. We do not know if our vacuum is truly false. Measurements of the Higgs boson and other fundamental particles suggest we might live in a metastable state, a plateau that could last almost forever, but is not completely unshakable. Still, the odds are so remote and the timescales so vast that to dwell on them is almost beside the point. Physicists estimate that if such a decay is possible, it would likely take longer than the current age of the universe multiplied by unimaginable factors. In other words, not tomorrow, not in billions of years, but in a time span so long it defies ordinary language. Yet even as a speculation, vacuum decay teaches us something profound. It reminds us that the stage upon which existence unfolds may not be eternal. The laws we take for granted, the way particles behave, the way forces shape matter, may themselves be provisional. Reality is more like a balance than a foundation, more like ice than stone. And while the odds of a sudden switch are vanishingly small, the mere possibility changes how we think about the solidity of the cosmos. If you want an everyday metaphor, think of electricity in your home. You flick a switch, and the lights come on. You assume the wiring and circuits are reliable, always there, always working. but hidden in the walls are fragile wires that could, in theory, fail. You rarely think about them because they almost never do. In much the same way, the universe's laws are usually invisible to us, quietly dependable. Only in the thought experiment of vacuum decay do we pause to realise how much we trust in their constancy, and how strange it would be if that constancy ended. There is also a certain poetry in imagining such an ending. Unlike the endless chill of entropy, or the fiery collapse of a crunch, vacuum decay is pure transformation. The universe does not fade or burn, it changes costume mid-performance. One story stops, another begins, even if no audience is there to see the curtain rise again. The image may be unsettling, but it also carries a whisper of possibility, that the cosmos is larger, stranger, and more layered than we can know, and that what seems final may only be a chapter in a deeper book. So when you hear the phrase vacuum decay, do not imagine a nightmare. Imagine instead the softest of switches, a transition you would never feel, a moment when the universe sighs and turns a page. It is not likely to happen, not within any span that matters to us, but as an idea, it invites us to see reality as something more delicate, more dynamic than stone. The floor beneath us is steady enough to last longer than stars, longer than galaxies, but still, perhaps not forever. When you sit down to play a familiar game, perhaps chess or cards or a simple board game, you trust that the rules are steady. A knight in chess always moves in an L shape. A heart is always a heart in a deck of cards. The game works only because everyone agrees on the rules. Now imagine if, halfway through the match, the rules shifted. Suddenly pawns moved backward, the value of a king was altered, or the suits in the deck transformed into something you had never seen before. The entire game would unravel, not because the pieces had disappeared, but because the rules that gave them meaning had been rewritten. This is the image that helps soften the abstract idea of vacuum decay. It is not simply the vanishing of stars and galaxies. It is the deeper thought that the very laws of physics, the rules that tell particles how to move, how to interact, how to combine, could one day be replaced. What we call constants may not be as constant as they appear. The charge of an electron, the mass of a proton, the strength of the forces that glue atoms together, could all, in an instant, change into new values. The universe we know would be transformed into something unrecognisable, not by destruction, but by redefinition. What would that look like? It is difficult to say because our imagination is tethered to the physics we know, but scientists speculate gently about the possibilities. In a true vacuum, atoms as we understand them might not exist at all. The electromagnetic force could change so that electrons could no longer orbit protons. The strong force could weaken or strengthen in ways that dissolve nuclei. Chemistry itself might vanish, because the patterns that allow elements to bond and form molecules would no longer function. In such a universe, matter as we know it would not form. It would be a stage without actors, or perhaps with actors so alien that we could not recognise the play. One way to think of it is in terms of recipes. Imagine baking bread. You rely on certain proportions, flour, water, yeast, combined in just the right way. Now imagine the rules of chemistry shifting so that yeast no longer causes dough to rise or flour no longer binds. You might still have ingredients, but the recipe would never come together. The bread would never exist. That is what a shift in the laws of physics would mean for the cosmos. The ingredients may still be there, but the recipe that builds stars, planets, and life would not. From a cosmic perspective, this would be a clean ending. No drawn-out cooling, no fiery collapse. Just a quiet replacement of the rulebook. Whatever emerges in the new vacuum, if anything at all, would be governed by a physics we cannot predict. It may be utterly barren. It may be vibrant in ways we cannot picture. It may be something so different that the word universe hardly applies. But to us within this one, the story ends the moment the switch is made. It is worth remembering that such speculation arises not from fantasy, but from the mathematics of quantum fields. The Higgs boson, discovered in 2012, gives mass to particles. The exact value of its mass hints that our universe may be perched on a plateau of stability, but not the deepest one. That means our vacuum might be metastable, long-lived, but not eternal. Like a ball resting in a shallow hollow on a hillside, it could remain there for trillions upon trillions of years. But one day, a quantum fluctuation might nudge it over the edge, sending it rolling into a deeper valley. That deeper valley is the true vacuum, and the roll into it would be the rewriting of the rules. There is a strangeness here, because the odds of such a transition are unimaginably low. On human scales, it is so unlikely as to be irrelevant. Even on cosmic scales, it might never happen. And yet, the possibility adds a layer of humility to our understanding of existence. We tend to think of the laws of nature as granite foundations, immovable and eternal. To realise they could be provisional, contingent, waiting to be revised, is to glimpse how fragile even the deepest parts of reality may be. Does this make the universe seem less stable, less comforting? Perhaps at first. But there is another way to see it. If the laws can change, then existence is more dynamic than we thought. It is less like a rigid monument and more like a story unfolding, with twists we cannot foresee. Stories, after all, are not diminished by their endings or their surprises. They are enriched by them. Some philosophers and physicists have even wondered whether such transitions could be a form of rebirth. If our universe ended in vacuum decay, the true vacuum might allow a new kind of structure, a new version of physics where matter and energy dance differently. Perhaps no stars, no galaxies, no people, but perhaps something else, something just as intricate. The thought is speculative, but it reveals an important truth. We cannot declare with certainty what follows when the rules are rewritten. We can only acknowledge that the possibility exists, and that possibility itself is a kind of wonder. So when you hear about vacuum decay, you need not imagine catastrophe in the usual sense. Instead, think of it as the quietest of shifts, the unseen switch of a cosmic game into new rules. One moment the universe plays by the laws we know, the next it is something else entirely. We would never notice, because notice requires continuity, and continuity would be gone. It would not be a scream or a collapse. It would be the softest click of a switch, the turning of a page we never get to read. On a clear night, if you look up at the sky, it is tempting to think of the universe as steady. The constellations seem fixed. The Milky Way drifts slowly overhead, and the stars give the impression of permanence. For most of human history, that is how the cosmos was understood. Unchanging, eternal, a backdrop against which life unfolded. But in the last century, astronomers have uncovered a different truth. The universe is not static. It is expanding, and not only is it expanding, it is doing so faster and faster, driven by something invisible, something we call dark energy. The discovery began in the 1920s, when Edwin Hubble measured the motions of distant galaxies. To his surprise, the farther away a galaxy was, the faster it seemed to be receding from us. The universe was not holding still, it was stretching, like dots on the surface of a balloon being blown up. This alone was a revelation, but the deeper shock came 70 years later, in the 1990s, when two teams of astronomers set out to measure whether that expansion was slowing down under the pull of gravity. After all, galaxies contain mass, and mass means attraction. The natural assumption was that the universe, having exploded outward in the Big Bang, would gradually decelerate, like a ball tossed upward that slows as gravity tugs it back. To test this, astronomers turned to supernovae, specifically a kind known as Type 1a. These are stellar explosions that occur in binary systems when a white dwarf steals too much matter from its companion and collapses into a runaway reaction. The remarkable thing about these supernovae is that they all explode with roughly the same intrinsic brightness. That makes them excellent standard candles. By comparing how bright they appear to us with how bright we know they truly are, we can measure their distance. And by measuring their redshift, the stretching of their light as the universe expands, we can determine how fast they are receding. The results were astonishing. Instead of slowing down, distant supernovae appeared dimmer than expected, meaning they were farther away than gravity alone could explain. The expansion was not decelerating, it was accelerating. The universe was not a ball tossed upward, it was more like a balloon, inflating faster as time passed. Something unknown was pushing space apart. To give this mysterious force a name, scientists called it dark energy. Dark, not because it is sinister, but because it is invisible and poorly understood. We cannot see it directly. We only infer it from its effect, the speeding up of cosmic expansion. Estimates suggest that dark energy makes up nearly 70% of the total energy content of the universe. Ordinary matter, the atoms in stars, planets, and people, accounts for less than 5%. Everything familiar, from mountains to music, is a tiny fraction compared to the quiet dominance of dark energy. What exactly is it? Here the story becomes delicate. One possibility is that it is a property of space itself, something Einstein once described in his equations as the cosmological constant. In this view, even empty space has energy, and as the universe expands, more space means more of this vacuum energy, driving further expansion. Another possibility is that dark energy is not constant, but dynamic, a field that changes over time, waxing and waning like a hidden tide. These subtler models go by names like quintessence or phantom energy, and while they remain speculative, they open the door to very different cosmic futures. If dark energy is steady, the universe drifts toward heat death. If it grows stronger, the big rip might await. If it weakens, perhaps even a crunch is possible. For now, the evidence leans toward constancy. The data from supernovae, the cosmic microwave background, and galaxy surveys all suggest that dark energy behaves very much like Einstein's cosmological constant. That points us toward a universe that expands forever, slowly cooling, sliding into stillness. But the fact that such a vast fraction of reality is invisible and uncertain is humbling. We live in a cosmos whose fate is written by something we cannot yet define. To bring this closer to home, imagine standing by the shore as the tide comes in. You see the water creeping up the sand, wave after wave. You know the tide is rising, but you cannot see the force behind it, the pull of the moon on the ocean. Dark energy is like that lunar pull. You do not see it directly. You see galaxies moving faster apart as if carried on a tide of space itself. The acceleration is the wave. The cause is hidden, but its effect is undeniable. There is a gentle irony here. For centuries, philosophers and scientists wondered what held the universe together. Now we wonder what drives it apart. And the answer so far is silence. A force without colour, without form, a breath too vast for our senses to detect. That silence is not frightening, though. It is the quiet reassurance that we still live in a universe full of mystery, a universe that has not yet revealed all its secrets. So when you hear the phrase, dark energy, do not think of menace. Think instead of the unseen breeze that keeps a sailboat moving even when you cannot feel it directly. Think of the tide pulling quietly at the shore, or the faint push of wind against your back as you walk. It is gentle, steady, inexorable, and it is shaping the ultimate fate of the cosmos, even now, as you lie here listening, as galaxies slip farther away in the night. When you stand beside a river, you can often see its motion long before you hear it. A line of drifting leaves, or a ripple on the surface, reveals that the water is moving, even if the current is subtle. Now imagine you're standing on the shore of the universe itself, watching galaxies the way you would watch leaves on a stream. You expect their motions to follow a certain pattern, each drawn by the pull of local gravity, each carried by the overall expansion of space. Yet in the late 2000s, astronomers noticed something puzzling. A large number of galaxies seem to be drifting together in the same direction, as if carried by a current flowing beneath the visible cosmos. They called this strange phenomenon dark flow. The discovery came from studying the cosmic microwave background, the faint afterglow of the Big Bang. This radiation, spread evenly across the sky, carries subtle imprints of temperature differences that reveal the motion of galaxies through space. By analysing clusters of galaxies against this backdrop, scientists thought they detected a coherent drift, an enormous bulk flow of matter moving toward a point in the sky. The scale was staggering. We're not talking about a few galaxies or even a single cluster, but hundreds of millions of light-years of structures, all sliding in the same cosmic direction. At first, the idea was met with both excitement and caution. If true, dark flow suggested that something beyond our observable horizon was tugging at our universe. Perhaps a massive structure outside the region we can see, something larger than any cluster or supercluster, was exerting its gravitational pull. Or perhaps the effect hinted at something even stranger, a neighbouring universe brushing against ours, or remnants of ancient conditions imprinted from before the Big Bang. The thought that our cosmos might be influenced by realms beyond sight was both thrilling and unsettling. But science thrives on repetition, on testing and retesting what appears to be true. As more data arrived, particularly from the Planck satellite, the case for dark flow weakened. Planck's sensitive instruments did not confirm the same large-scale drift. The signal could have been an artifact, a product of measurement error, or the tricky business of subtracting noise from subtle cosmic signals. Today, dark flow remains debated. Some researchers still argue for its presence, others consider it a ghost of analysis rather than a real current. Yet even if dark flow itself fades as evidence, the question it raises lingers. What lies beyond our cosmic horizon? The universe we can see is limited by the speed of light and the time since the Big Bang. Beyond roughly 46 billion light-years in any direction, light has not had time to reach us. That boundary is like a hill beyond which the river flows out of sight. We can guess at what lies past it, but we cannot see directly. If there are vast structures beyond, enormous clusters, hidden currents, perhaps even other universes, their presence might subtly tug on the galaxies within our view. The metaphor of a river is helpful here. You can stand at one bend and see the leaves floating past. You might even feel the tug of the current if you wade in. But the source of that current, perhaps miles upstream, remains hidden. You only infer it by the motion around you. Dark flow, whether real or not, invites us to think of the universe in the same way, as part of a larger stream, with unseen causes shaping the motions we can observe. What makes this idea so evocative is not only the possibility of hidden structures, but the reminder of how small our cosmic map is. The observable universe feels immense, trillions of galaxies, billions of light-years across, and yet it may be just a patch, one bend in a river that stretches beyond imagination. To detect even the hint of something larger is to remember that our perspective is always partial, our horizon always limited. For listeners lying in bed, this thought can be both humbling and strangely comforting. The mysteries of physics are not confined to laboratories or equations. They are stitched into the very motion of the galaxies overhead, into the patterns of light that bathe the night sky. When you gaze upward, you are not only seeing stars, you are glimpsing the faint signs of deeper currents. Whether or not dark flow proves real, the curiosity it sparks is a gift, encouraging us to wonder what lies beyond what we can see. Even within the debate there is poetry. The WMAP satellite's data suggested a current. The Planck mission contradicted it. Perhaps the truth lies somewhere between. Perhaps the signal was too faint to measure cleanly. Perhaps there are subtler flows waiting to be uncovered. Science is not a final word, but a conversation with the cosmos, a dialogue that continues as our instruments sharpen and our questions grow. If dark flow exists, it would mean the universe is not entirely uniform, that some deeper asymmetry tugs on everything within sight. If it does not, then the cosmos is more even than we imagined, and our horizon remains a clean, quiet boundary. Either way, the story reveals how sensitive we have become to whispers in the dark. A few degrees of temperature difference in a faint glow from the early universe can spark entire new visions of cosmic fate. So, the mystery of dark flow is not about certainty. It is about wonder. It is about watching the leaves on the river and wondering what shaped the current beyond the bend. It is about looking up at the galaxies and asking whether something unseen is guiding them. And it is about remembering that even in our age of satellites and observatories, the universe keeps its secrets close, inviting us to listen, to measure, to imagine, but never giving away the whole story at once. If you stand in a field and toss a ball into the air, there are only a few possible outcomes. If you throw it gently, gravity wins, and the ball arcs upward before falling back into your hands. If you throw it harder, it rises higher, takes longer to pause, but still returns to Earth. And if you had the strength to throw it with extraordinary speed, it might escape entirely, slipping free of Earth's pull, never to fall back again. This simple image captures the essence of the universe's fate. The cosmos itself is the ball, its expansion the upward throw. Gravity tugs inward, expansion pushes outward, and the balance between them determines whether the universe falls back into itself, coasts to a halt, or escapes into endless flight. For much of the 20th century, cosmologists thought the question was balanced on the edge of a knife. Did the universe contain enough matter to pull itself back together, to end in a great crunch? Or was there too little matter, so that expansion would continue forever, slowing but never stopping? The debate was not only scientific but philosophical, because the answer determined the shape of time itself. A closed universe destined to collapse would be cyclical, beginnings and endings folded together, an eternal heartbeat. An open universe destined to expand forever would be a line stretching into infinity, an arrow with no return. The measure of this cosmic throw came down to density, how much matter and energy fill space. Cosmologists speak of a critical density, the exact balance point. If the universe contained more than this, gravity would eventually overpower expansion. If it contained less, expansion would continue indefinitely. For decades, astronomers tried to measure the total mass of galaxies, the hidden halos of dark matter, the glow of cosmic background radiation, all in the hope of pinning down whether the universe was heavy enough to fall or light enough to fly. The evidence seemed to sway back and forth. One survey would suggest there was just enough matter to pull things back. Another would find too little, pointing to endless expansion. It was like listening to the back and forth of a lullaby, a tune rising and falling without resolution. Then, in the 1990s, the discovery of dark energy added a new note. It turned out the universe was not merely coasting outward, it was accelerating. That meant the balance was not a knife edge at all, but a tide already rushing away. Even if matter had been abundant enough to halt expansion, dark energy changed the game, tilting the balance firmly toward flight. Still, the concept of balance remains important, because it reminds us how delicate the cosmic forces truly are. Expansion and gravity are not equal partners, they are mismatched, tugging in different ways across unimaginable scales. Gravity gathers matter, pulling galaxies into clusters, stars into orbits, planets into circles. Expansion pushes space itself outward, carrying galaxies apart, stretching the fabric that gravity tries to weave together. It is like two children playing tug-of-war on a rope that is also slowly growing longer. Neither side can claim total victory without reshaping the whole game. When we step back and look at the evidence today, it is clear that expansion dominates. Measurements of the cosmic microwave background, the distribution of galaxies, and the behaviour of distant supernovae all point to a universe that will not collapse. The critical density is not reached because while there is matter and plenty of it, there is not enough to counteract the accelerating expansion. The scales are tipped. The ball has been thrown with escape speed, and the universe is not coming back. For us, this conclusion carries two kinds of meaning. Scientifically, it points to the heat death as the most likely fate. Galaxies drifting apart, stars burning out, energy spreading thin until nothing remains to change. But poetically, it highlights the fragility of balance. The forces that shape the cosmos are vast, yet their relationship is delicate. A slightly different density of matter, a slightly different character of dark, energy, and the fate of the universe would be entirely altered. It is as if reality is tuned with exquisite precision, a symphony that could have ended in thunder, but instead drifts towards silence. To make this more tangible, imagine a candle balanced on the edge of a table, a breath of wind to one side and it falls, a nudge to the other and it stays. The universe too seems balanced on such edges, except the table is billions of light years wide and the candle burns for trillions of years. The fact that we can even measure these forces, that we can calculate the balance point, is a quiet triumph of human curiosity. From our small world, we have stretched our minds to weigh the cosmos itself, to ask whether it will fall or fly. And perhaps there is a kind of comfort in knowing that the balance is settled. We no longer wonder whether the universe will collapse in a fiery crunch. The evidence leans heavily toward expansion without end, toward the long, cold future we call heat death. This is not the most dramatic ending, but it is the one written in the silent acceleration we measure today. The universe will not roar to a close but fade, slowly, patiently, like a song that becomes softer until you strain to hear it and realise it has already ended. So the fragile balance between gravity and expansion is not merely a technical matter of equations. It is a meditation on the way endings are chosen. A little more matter, and we might have been headed for fire. A little less dark energy, and we might have coasted forever without acceleration. But here we are, balanced in the path that leads to quiet. It reminds us that the universe is both robust and delicate, both vast and finely tuned. And as you lie here, listening, you can feel the comfort of that balance. The cosmos is steady enough to hold you, yet subtle enough to invite wonder, forever balanced between the pull of gravity and the push of expansion, until the last notes of its story fade away. When we speak of eras in the life of the universe, we often picture grand beginnings, bursts of light, newborn stars, galaxies spinning into form. But the story also has its quieter chapters, when the brilliance fades and what remains are the remnants, the long-lived survivors of an age already past. Cosmologists call one such chapter the degenerate era, a time when the stars have burned out, the galaxies have dimmed, and the cosmos is filled not with fire, but with the leftovers of what once was. To imagine this age, picture walking through the ruins of a great city. Once there were lanterns glowing in every window, streets filled with voices and markets alive with colour. Now the streets are silent. The buildings stand but are empty. A few candles may still flicker here and there, but they are rare, isolated, and fading. The degenerate era is like that. A universe that once blazed with the light of stars, now quiet, filled only with remnants of what those stars left behind. The main characters in this dim chapter are white dwarfs, neutron stars and rogue planets. White dwarfs are the husks of stars like our sun, small, dense embers that once glowed with fading heat. In the degenerate era, they have cooled further. Their once bright surfaces darkened, radiating only a faint whisper of warmth. Neutron stars, the collapsed cores of massive stars, remain too, silent and compact, like cosmic diamonds scattered across the dark. Rogue planets drift as well, worlds that have been flung from their stars, wandering alone through interstellar night. None of these bodies shine in the way stars once did. They are not engines but relics, fossils of a more luminous past. The darkness does not mean absolute stillness, however. From time to time, something stirs. White dwarfs and neutron stars, though faint, still hold gravity's patient grip. Occasionally, in spans of time so long that they make human history seem like a blink, these remnants collide. Two white dwarfs might spiral together, releasing a brief blaze of energy, a flash in the endless dark. A neutron star may merge with another, creating ripples of gravitational waves that spread silently through the black. These events are unimaginably rare. So rare that in 1,000,000 years only one or two may occur in a galaxy. Yet each one is like a forgotten match struck in a cavern, a fleeting reminder of fire in an otherwise frozen silence. In a way, these sparks are more precious for their rarity. Imagine a desert night so long and cold that you never expect light again, and then, without warning, a single firework bursts against the sky. It would not change the desert, but it would change your memory of it. The degenerate era is filled with such improbable moments, scattered so thinly across time that they hardly matter to the universe as a whole. But to an observer, if any could exist, they would feel miraculous. To bring this closer, think of the embers of a campfire. Long after the flames have died, if you stir the ashes, sometimes a spark leaps free. The degenerate era is the cosmic equivalent of stirring the ashes. Occasional sparks, reminders of what once burned so brightly. They are not new beginnings, only echoes of the old. This age also reminds us of how slowly the universe moves on its larger scales. While stars live for billions of years, the degenerate era stretches across time so vast that words lose their grip. We measure human history in centuries, geological history in millions of years, stellar lifetimes in billions. But the degenerate era belongs to trillions and beyond. It is the slow turning of a wheel that we cannot see complete, a story whose sentences are written in units larger than any page we could hold. And yet, for all its stillness, there is something strangely peaceful about this chapter. It is not chaotic. It is not violent. It is simply quiet. A universe no longer busy with the labour of making stars, but resting among the remnants of those already made. The blackness of the sky, once filled with constellations, would be almost total. Only the faintest embers would remain far apart, their glow stretched thin by distance. The silence would be profound but not menacing. It would be the silence of a cathedral long after the choir has finished singing, still filled with memory even though the voices are gone. If we think of life in such an era, the imagination strains. Could any form of existence endure in such conditions? Perhaps machines, running on the faint energy of star remnants, could stretch out survival. Perhaps civilizations, if they existed, might harness the rare collisions of matter as their fuel. But these are speculations, and they remind us again of the scale of entropy's patience. Sooner or later the available energy diminishes. Even the most clever strategies would falter in the long dark. The degenerate era is not hostile so much as indifferent. It does not burn you, it simply forgets you. And yet in that forgetting there is perspective. The universe does not owe us permanence. It gives us moments, and those moments shine brightly against the backdrop of what comes later. Our sun will burn for billions of years. Our galaxy will spin for longer still, but in time, both will pass into this quiet age of remnants. When that happens, the story of brightness will be complete, and the cosmos will enter its long exhale. So the degenerate era is not only a chapter of science, but a meditation on memory. What remains after the flames? What echoes endure after the song? For the universe, the answers are white dwarfs. neutron stars, rogue planets, and the occasional spark of collision. For us, perhaps the answer is more personal, the recognition that even in endings there is beauty, even in silence there is story, and even in the dark there can still be a spark, however rare, to remind us of the light that once was. If you have ever seen a coal in the ashes of a fire, glowing faintly long after the flames have died, you have already glimpsed the destiny of most stars. They begin in brilliance, live in balance, and end as embers. For stars like our Sun, that ember is a white dwarf, a core of carbon and oxygen, dense beyond imagination, glowing softly with leftover heat. Over billions and trillions of years, those embers cool. They radiate their warmth into the vast emptiness until they no longer glow at all. When that moment comes, what remains is a black dwarf, a star that has not disappeared but has faded beyond sight, a diamond-like corpse adrift in eternal night. No black dwarf exists yet because the universe is still far too young. Even the oldest white dwarfs, formed in the earliest generations of stars, still glow faintly. To reach the point where they're truly cold, when their light has been entirely given back to space, requires timescales so immense they almost slip from meaning, 10 to the power of 15 years, or more. That is million billion years, long enough that even the word forever feels small beside it. And yet, if the universe endures, black dwarfs will one day be the most common objects in the sky, a sky with no light, only invisible stones floating in silence. To picture one is difficult. A black dwarf would be as dense as a white dwarf, so dense that a teaspoon of its material would outweigh mountains. Its surface would be smooth, hardened, crystalline, like a diamond the size of the Earth. But unlike a diamond that catches sunlight and glitters, a black dwarf would lie in perfect darkness, reflecting nothing, radiating nothing, colder than the space around it. It would be a monument to endurance, a relic that has waited out the heat of the stars, the light of the galaxies, and the fire of the universe itself. And yet, within these husks may lie one of the strangest possibilities in all of astrophysics, the idea of a black dwarf supernova. Normally, supernovae occur when massive stars collapse under their own gravity, or when a white dwarf accumulates too much material from a companion and ignites. But theoretical physicists have suggested that even a lone black dwarf, long after it has cooled, might one day explode, not because of fusion or collapse, but because of quantum tunneling, the strange ability of particles to bypass barriers and trigger reactions against all odds. In this scenario, after unimaginable spans of time, a black dwarf's atoms could undergo a spontaneous chain reaction, setting off a supernova-like explosion. It would not happen often. The probability is so low that each star would have to wait longer than the current age of the universe multiplied many times over. But in an eternity, even rare things can happen. And so, in that far-off age, when the universe is otherwise dark, a single black dwarf could ignite, briefly lighting up its corner of the cosmos in a final lonely blaze. Think of it like an abandoned city where every lamp has gone out, every fire has cooled. Then, one night, against all expectation, a single lantern flares to life, burns brightly for a moment, and then extinguishes again, leaving the city darker than before. That lantern would not change the fate of the city, but it would remind anyone watching, if anyone could watch, that fire once existed, and that even in silence surprise is possible. Of course, these black dwarf supernovae are speculation. We cannot test them now, nor will we ever witness one. They belong to a realm of time so distant that even black holes may have come and gone by then. But the idea itself carries a quiet kind of beauty. It means that even after the universe has forgotten light, after stars are long gone and galaxies scattered, there may still be rare and fleeting fireworks. The cosmos, patient as it is, may still save a spark for the very end. It also gives us a way to reflect on impermanence. The white dwarfs that exist now are the children of stars that lived billions of years ago, stars that formed when galaxies were young. They shine faintly, but they still shine. To imagine them as black dwarfs is to imagine their story completed, their energy fully given, and to imagine them exploding again after eons of silence is to imagine that even endings can contain surprises. If you hold a diamond ring or a crystal in your hand, you might think of these future relics. The atoms in that stone will outlast you, outlast the earth, outlast the sun itself. And in some inconceivably far-off epoch, when all else is dark, those atoms may still exist, locked in a cosmic diamond drifting through the night. The idea that matter can endure so patiently, that it can wait longer than galaxies, offers both humility and awe. So when we think of the black dwarf era, we are not picturing fireworks or chaos. We are picturing stillness, cold, and persistence. The universe becomes a graveyard of diamond corpses, silent monuments to stars. But within that graveyard, once in an unfathomable while, a single stone may flare, breaking the silence for a heartbeat before returning to it. That thought, improbable though it is a reminder that even in endings, the cosmos may whisper one last surprise. If the degenerate era is a universe of embers and shadows, the chapter that follows is a universe of anchors. For when the last faint white dwarfs have cooled, and the last neutron stars have ceased their rare collisions, what remains to dominate the cosmos are black holes. They are not new characters in this story. They were born long before, in the fiery deaths of massive stars, in the collisions of neutron stars, in the gradual swallowing of matter by gravity's patient hand. But in the distant future, after trillions upon trillions of years, they will be the most enduring structures left, the last landmarks in an ever emptier night. Black holes are often imagined as wild, destructive things, monsters devouring everything near them, and while they can indeed consume stars and gas clouds, their role in the late universe is quieter, almost solemn. With the cosmos emptied of most of its fuel, black holes have little left to feed on. They sit instead as silent giants, holding their gravity fields like invisible lanterns. If you could orbit one in that far-off time, you would not feel chaos but stability. Its gravity would guide you as predictably as Earth's gravity holds the moon. There would be no roar, no tearing, just a patient, curved space, a path traced in darkness. In a way, black holes will be the guardians of memory. While stars fade and planets crumble, black holes endure. They are the last archives of matter, compressing what they swallow into singularities hidden behind horizons. They store, in a sense, the histories of what has fallen into them, though whether that information is preserved or lost remains one of the deepest puzzles in physics. To imagine a universe of black holes is to imagine a cosmos, where all that remains are locked doors, each holding secrets behind a veil that no one can open. Picture a quiet desert at night. The sands stretch endlessly and the air is cold. But here and there stand enormous stones, dark monoliths, unmoving, indifferent. That is what the black hole era will resemble, a universe emptied of light, punctuated only by these silent monoliths of gravity. They do not shine, but they shape. They do not speak, but they hold. It is important to remember that not all black holes are equal. Some are the remnants of single stars, only a few kilometers across. Others are the giants at the centers of galaxies, millions or billions of times the sun's mass. These supermassive black holes, in particular, will define the late universe. Even as their galaxies fade around them, they will remain, like cathedral pillars standing after the roof has collapsed. For trillions of years, they will be the largest, most stable structures the cosmos can offer, and yet even in this quiet, interactions will still happen. Black holes may merge, spiraling into one another, releasing enormous bursts of gravitational waves. These ripples, faint but vast, will roll across space, carrying away some of the last great energies of the universe. Such events will be rare, scattered across spans of time that dwarf all of human history. But they will happen, and in each, the universe will whisper of its past dynamism, even as it settles into long calm. Imagine listening to a piece of music that has slowed almost to silence. Most of the instruments have stopped, but now and then a deep drum sounds, low and resonant, reminding you that the song is not entirely over. Black hole mergers will be like that, rare, deep notes in a fading symphony. If one wonders what it might feel like to live in such a time, the thought quickly slips beyond reach. There would be no stars to warm a planet, no galaxies to cluster together, no sunlight to measure days. The night sky would be empty, save for the faint gravitational influence of these unseen giants. To exist in that age would be to live in a universe stripped bare, with only the invisible pull of black holes to remind you that structure still exists. The presence of black holes in this role is poetic as well as scientific. They are born in endings, forged in collapse. They are places where matter itself seems to vanish, where light is caught and never released. And yet, in the long sweep of cosmic time, they are also symbols of endurance, of persistence. Everything else fades, but black holes remain, patient and enduring. They may not be hospitable, but they are faithful, standing when all else has fallen. So, as we imagine the black hole era, let us not picture only menace. Let us see instead the calm stability they bring to the late universe, their role as anchors in a sea of nothingness. The cosmos may by then be empty of stars, but it will still have form, still have weight, still have a quiet structure. The night may be dark, but it will not be formless. The black holes will keep vigil, waiting, holding, shaping, until even their patience runs out. When most people imagine black holes, they picture endless endurance, objects so dense and unyielding that nothing, not even light, can escape. To think of them fading seems almost contradictory, like imagining a mountain dissolving into mist. Yet even the most patient giants of the cosmos are not immortal. Over spans of time so vast they stretch the imagination thin, black holes too will vanish, leaving behind not the roar of collapse but the whisper of heat. This strange fate was first suggested by Stephen Hawking in the 1970s. Until then, black holes were thought to be absolute traps, swallowing everything and releasing nothing. But Hawking showed, through the delicate mathematics of quantum fields, that black holes are not entirely silent. On the edge of their horizons, where space curves so steeply that escape seems impossible, pairs of virtual particles flicker into being. Normally such pairs annihilate instantly, disappearing as quickly as they appear. But near a black hole, one particle can fall inward while the other escapes, carrying away a tiny amount of energy. To a distant observer, it looks as though the black hole is radiating. This gentle glow is what we now call Hawking radiation. The effect is unimaginably faint. For a black hole the mass of the sun, the radiation is colder than the cosmic microwave background, too small to detect in the universe as it exists today. But the cosmos is patient. The microwave background will continue cooling as expansion stretches its light into longer and longer wavelengths, and as the background cools, the radiation from black holes will one day stand out. Slowly, almost imperceptibly, they will lose mass. Each escaping particle subtracts from their energy, and over trillions upon trillions of years the giants will shrink. The timescales are beyond our instinct. A black hole of stellar mass may last for 10 to the power of 67 years. A supermassive black hole, like the one at the centre of our galaxy, may endure for 10 to the power of 100 years. These numbers are so vast that they almost feel like eternity itself. Yet even eternity, when broken into steps, eventually runs its course. In the end, no black hole can resist the slow leaking away of its energy. The final moments of a black hole's life are not quiet. As it shrinks, it grows hotter, radiating more intensely. What was once faint becomes fierce. In the last fractions of a second, a black hole releases a burst of energy brighter than 1,000,000 suns. This is not the long glow of a star, but a final firework, a sudden flare that consumes what remains. Then, as quickly as it came, the black hole is gone, its horizon vanished, its secrets evaporated into radiation. To imagine the universe in that time is to imagine a night filled with occasional sparks. For eons the cosmos is quiet. Then somewhere, far away, a black hole evaporates in a brilliant flash, like lightning illuminating a stormless sky. Then silence returns. Another eon passes, another spark. Slowly, patiently, the giants fade, until at last there are no black holes left, only the faint uniform afterglow of their passing. There is a strange poetry in this. Black holes are born from endings, the collapse of massive stars, the merging of dense remnants. They are symbols of finality, of no return. Yet even they are not immune to impermanence. The same universe that gave them form will also in time take them away. Nothing is exempt. The mightiest anchors will eventually dissolve into whispers of radiation, their grandeur reduced to a thin mist. But far from making them less mysterious, this makes black holes more profound. They are reminders that endurance itself is temporary, that even what seems eternal is only part of a longer story. To think of them evaporating is to see the cosmos not as a static sculpture, but as a flowing river, where even the stones are worn down by time. For anyone trying to picture this on human scales, think of an ice cube left in a room. At first it seems solid, immovable, but given enough time it melts away, not with a crash, but with a slow seeping. Hawking radiation is the melting of black holes. The process is slower than any patience we could hold, but the principle is the same. What appears permanent is only temporarily frozen. The final bursts of evaporating black holes will also mark the last truly energetic events in the universe. After them, nothing large will collapse, nothing brilliant will flare. The fireworks will be over. What remains will be a diffuse sea of low-energy particles, stretching thin across infinite space. In that sea, there will be no more anchors, no more structures to gather matter or light. The giants will have kept their vigil as long as they could, and then they too will have gone. And so the black hole era ends not with destruction, but with fading. The guardians of gravity release their last warmth, the final embers in a night that has stretched beyond measure. Once they are gone, the universe enters its next chapter, a chapter without landmarks, without beacons, without anything to break the silence. It is the beginning of the dark era, the quietest of all. But for now, in your imagination, hold on to the image of those giants waiting, patient, timeless in their watch. Picture their horizons shimmering faintly with hawking radiation, like the edges of lanterns glowing with a light too faint to see. Know that even the strongest must one day yield, but that in their yielding they give the universe a last gift. A flare, a whisper, a final reminder that nothing lasts forever, not even the darkness itself. If you hold a stone in your hand, or a cup, or even look at your own body, you're seeing something built from protons. These tiny particles along, with neutrons and electrons, form the atoms that make up everything we know: mountains and oceans, bones and breath, stars and planets. For most of physics, protons have been treated as permanent, unchanging, the sturdy bricks of matter. Stars may live and die, galaxies may scatter, but protons seemed eternal. Yet some theories suggest even these building blocks are not forever. Over unimaginable spans of time, they too may decay, dissolving the material universe grain by grain until nothing solid remains. To picture this, imagine a sand castle by the sea. At first it looks strong. its towers sharp against the sun, its walls smooth. But the tide is patient. With every wave, a few grains slip away. The structure remains for a long while, but eventually as grains vanish one by one, the castle collapses into the beach. Proton decay is the tide of the universe, slowly eroding its castles of matter until what was once sturdy dissolves into a featureless shore. The idea of proton decay comes from attempts to unify the fundamental forces of physics. In our current understanding, 3 of the 4 forces, electromagnetism, the strong force that binds atomic nuclei, and the weak force that governs radioactive decay, may be parts of a larger whole, described by Grand Unified Theories, or GUTs. In some of these models, protons are not perfectly stable. Instead, they have a finite, though extraordinarily long half-life. Given enough time, perhaps 10 to the 34 years, perhaps longer, half the protons in the universe could decay into lighter particles, such as positrons and photons, leaving behind radiation instead of matter. This is far beyond anything we could ever observe directly. Experiments on Earth have searched for proton decay in enormous underground detectors, waiting for even a single particle to betray its instability. So far, none have been seen, suggesting that if decay occurs, it must take vastly longer than the current age of the universe, and yet the possibility remains. The equations whisper that even the bricks of matter may one day crumble, if only we wait long enough. What would this mean for the late universe? At first, not much would appear to change. Stars will already have died, black holes will already be fading. But as the ages roll on, the slow erosion of protons would eat away at everything left. White dwarfs, neutron stars, rogue planets. Any object made of matter would dissolve from within. Even atoms themselves would disintegrate, their cores turning to radiation. The universe, once filled with stones and steel, oceans and life, would become a place with no structure larger than a flicker of light. This vision is unsettling, but also strangely gentle. It is not a sudden collapse, not a violent tearing apart. It is a patient unmaking, a tide too slow to notice, yet too steady to resist. Imagine walking into a great library, its shelves filled with books, each volume containing a story. Then imagine that one by one the letters on the pages fade. The books remain on the shelves, but their words vanish, until the stories are lost and the volumes are blank. Proton decay would do the same to the universe, leaving the shelves, but erasing the content until only emptiness remains. And yet there is a quiet beauty in this image as well. The universe has always been a story of transformation. Stars turn hydrogen into helium, forging elements in their cores. Supernovae scatter those elements, seeding planets and life. Black holes swallow matter, then release whispers of it as radiation. If protons decay, then even the foundation of matter participates in this endless cycle of change. Nothing is exempt from impermanence, not even the smallest bricks. The timescales involved are so large that they almost defy comprehension. 10 to the power of 34 years is a span with 34 zeros, a number that makes the lifespan of stars look like seconds in comparison. For perspective, if the age of the universe today were a single breath, the time until proton decay would be a mountain of breaths taller than the sky. And yet, physics invites us to imagine even this, because in imagining it we glimpse how vast time truly is and how patient the universe can be. Some physicists suggest that even if protons decay, not all is erased. Perhaps new kinds of structures, exotic and strange, could form from the particles left behind. Perhaps the universe would become a mist of faint light, photons drifting endlessly, no longer bound into atoms but still filling space. It would be a cosmos without solidity, without rocks or bones or worlds, but not without presence. Like fog on a winter morning, thin and insubstantial but still there. To think of such a future is not to invite despair, but perspective. You are living in a moment when protons seem eternal, when atoms hold firm, when the world beneath your feet is solid and reliable. The cup in your hand, the chair you rest upon, the air in your lungs, all are possible because matter endures. That endurance, however temporary in the grand arc, is what makes our existence possible. The very fact that protons last as long as they do is why stars can shine, why life can persist, why stories can be told. Their eventual fading, if it happens, only reminds us of how extraordinary their longevity already is. So the dissolving world of proton decay is not a nightmare, but a meditation. It tells us that permanence is an illusion, that even the smallest things are part of the dance of change, and in that realization lies a gentle wisdom, that our present solidity, the feel of earth, the strength of stone, the rhythm of life, is a gift of this fleeting moment in cosmic time. It will not last forever, but it lasts now, and now is enough. Picture the world on a foggy morning. The outlines of buildings blur, the trees stand as silhouettes, and the air feels thick, muted, as though the usual details have been washed away. Now imagine that fog never lifts, and that it stretches not across a city or a forest, but across all of space. This is how physicists sometimes describe the final chapter of the universe after black holes have evaporated, after protons, if they are unstable, have dissolved into radiation, and after every structure we can name has disappeared. They call it the dark era, though it might just as easily be called the era of fog, the age when the universe becomes a thin, endless haze. In this epoch, the grand actors of the cosmos are gone. No stars burn, no galaxies spiral, no black holes lurk as silent anchors. What remains are particles scattered across an infinite stage, spread so widely that they barely interact. Photons, quanta of light so stretched by expansion that their energy is almost zero, drift like dust motes in an abandoned hall. Neutrinos, ghostly and almost without weight, pass through the fog without leaving a mark. If protons have decayed, then the last traces of matter are gone, replaced by a sea of faint radiation. If they have not, then what lingers are inert, isolated particles, frozen in their stillness. In either case, the difference is cosmetic. The Dark Era is an age without contrasts, without engines, without story. To appreciate how strange this is, think of what gives our world its texture. The warmth of sunlight, the coldness of night, the solidity of earth, the sparkle of stars overhead, all are contrasts. Heat flows from hot to cold, light shines against shadow, matter clumps against void. These differences drive every process. But in the Dark Era, those contrasts vanish. Energy is spread too evenly, like butter smeared across bread until there is no thickness left anywhere. Without gradients, no change can occur. Without change, time itself becomes slippery. Seconds may still pass, but with nothing to distinguish one from another, they blur together, meaningless in their uniformity. The Dark Era, then, is not merely about darkness, but about silence. Not the silence of a library, where stories still whisper from the shelves, but the silence of an empty desert after the wind has stopped blowing. It is a silence so complete that it is difficult to imagine any observer left to notice it. Perhaps rare quantum fluctuations might stir now and then, producing a fleeting particle or even the notorious thought experiment of a Boltzmann brain. But these are not lives. They are brief sparks that vanish as quickly as they appear, like static on a blank screen. For us, thinking about such an era requires imagination that is less about detail and more about absence. Imagine walking through a city where not only are the lights out, but the buildings have melted away, leaving only a faint mist where streets once ran. Imagine listening to a song where every note has been stretched into infinity, until it becomes an unbroken hum you can no longer distinguish as music. Imagine holding a book where the ink has faded from every page, leaving only the ghost of letters you cannot read. This is the kind of world the Dark Era would be. Not destroyed in fire, not crushed by gravity, but slowly diluted until nothing recognizable remains. It is easy to think of this as bleak, but there is another way to hear it. The Dark Era is also a kind of rest, a final exhale. The universe, after its long and tumultuous life, has given everything it could. It has flared in stars, whirled in galaxies, collapsed in black holes, whispered through radiation. It has produced elements, planets, oceans, and at least one world where beings could wonder about it all. Having exhausted its possibilities, the universe settles into stillness. Like a traveller who has walked a great distance, it finally sits down, no longer striving forward, simply existing in peace. And though the Dark Era seems featureless, it carries within it the memory of all that came before. The photons drifting through it are not new. They are the stretched-out descendants of light that once blazed in stars and supernovae. Each is a remnant, a ghost carrying with it the story of the fire that birthed it. The fog is not nothing. It is history thinned to transparency, memory diluted until it feels like emptiness. To a human mind, this future is so distant it can feel unreal. We measure our lives in decades, civilizations in centuries, planets in billions of years. The Dark Era lives in spans so large that even black hole lifetimes are just prelude. To imagine it is less an exercise in science than in meditation. You cannot truly picture it, any more than you can picture infinity. You can only let the thought wash over you. A lullaby of stillness, a story that says, eventually everything rests. And perhaps that is the gift of thinking about the Dark Era. It reminds us that contrast is what makes our present vivid. The warmth of a hand, the sound of rain, the glimmer of starlight, all exist because we are still in an age of difference. Time is still textured, energy still flows, light still shines. To know that these things will one day dissolve into featureless fog does not diminish them. It makes them more precious. The fog is a canvas, and we live in the brief moment when the paint is still bright. So when you hear about the Dark Era, do not think only of absence. Think of it as the ultimate stillness, the silence at the end of a song, the fog after the last lantern has gone out. It is not terrifying. It is simply the natural closing of the universe's long day, a night that stretches without end, calm, quiet, and complete. When we think about endings, we often imagine the disappearance of things. Books burning, buildings collapsing, stars fading. But there is another and subtler kind of ending, one that does not take away the objects themselves, but erases the patterns that give them meaning. It is the loss of information. A book without words is still a book, but its story is gone. A melody with every note, stretched into sameness, is still sound, but it is no longer music. In the final chapters of the universe, after stars and black holes and even protons have dissolved, this is what remains to fade. The information that once told the story of the cosmos. In physics, information is more than just facts written on a page. It is the arrangement of things, the patterns of matter and energy. The difference between ice and water is not the molecules, they are the same, but the way they are organized. The shape of a galaxy, the spin of an electron, the orbit of a planet, even the structure of DNA in a cell, all are forms of information. They tell us how the pieces of the universe are arranged, how energy and matter dance together. As long as structures exist, so does information. When stars shine, they carry the record of fusion in their light. When black holes swallow matter, they seem to hold information at their horizons. When you speak, the air carries vibrations that encode your words. The universe is a vast library, not of paper and ink, but of arrangements, patterns written in particles and waves. But libraries can be emptied, and patterns can fade. In the Dark Era, when matter has decayed and black holes have evaporated, what remains is a thin fog of particles and radiation, stretched evenly across space. With everything so uniform, no differences remain to tell one place from another, one moment from another. It is as if every book in the library has been stripped of its letters, leaving only blank pages. The shelves are still there, the paper still intact, but the stories are gone. This end is more final than the loss of stars, because stars at least tell stories of their burning. It is more final than the fading of galaxies, because galaxies leave traces in their shape and movement. The end of information is the erasure of memory itself. Without patterns, the universe no longer contains any record of what it once was. The great chain of cause and effect that stretched from the Big Bang through galaxies and life and thought dissolves into featureless fog. The thought unsettles some physicists because it touches on deep questions about whether information can ever truly be destroyed. Quantum mechanics suggests that information, in some form, is always preserved. Even if matter changes, the details of its transformation remain encoded in subtle ways. But in practice, as entropy increases, information becomes so scrambled, so diffuse, that it may as well be lost. The pages are still technically there, but no one could ever reconstruct the words. The difference between technical survival and practical erasure is like the difference between a melody scattered across a billion instruments out of tune and a melody played clearly on a piano. One exists only in theory, the other in experience. For those of us trying to imagine this future, the metaphor of the last library may help. Walk through halls where shelves stretch endlessly. Every book is present, but every page is blank. The smell of paper remains, the weight of volumes still in your hands, but the content, the meaning, is gone. You're surrounded not by stories, but by silence. This is the universe without information. It exists, but it says nothing. And yet, even in contemplating this, there is perspective to be gained. We live in the opposite of that age. Our universe is full of patterns. The air vibrates with sound, carrying voices and music. Light streams from stars, encoding their temperatures and motions. The earth spins, giving us day and night, a rhythm that has shaped every culture. Even your own thoughts are patterns of information, neurons firing in arrangements that form memories, hopes and dreams. To know that information may one day fade is to treasure the extraordinary richness of it now. It is also worth noting that the fading of information is not unique to the universe. You encounter it every day in smaller forms. A photograph left in sunlight loses its image. A memory grows faint with age. A song forgotten is no longer music, though the notes could still be played. Entropy touches all levels, from the cosmic to the personal. The universe's end is simply the ultimate example, where not only photographs or songs are lost, but the entire cosmic record itself. Some find comfort in speculation that perhaps information never truly dies. Perhaps it is preserved in subtle holograms at the edges of black holes, or in the deep mathematics of space-time itself. Perhaps in ways we cannot yet grasp, the memory of the universe will remain encoded forever, invisible but real. Whether or not this is true, the thought is a kind of lullaby, that nothing is truly lost, only hidden, waiting in silence. But even if information is gone in every practical sense, the story of the universe is no less meaningful. Meaning exists in the telling, in the experiencing. You do not need the final chapter to validate the earlier ones. A song is beautiful even if its last note fades into quiet. A day is precious even if night follows. The universe too is meaningful now while its patterns still sing. Its library is still full of words. Its pages are still written with light. So when we think of the end of information, let us not dwell on blankness, but on the miracle of meaning we hold now. To live in an age when the cosmos is still rich with patterns, when galaxies still spiral and stars still burn, is to live in a fleeting chapter before the shelves are emptied. It is not cause for despair, but for wonder. For every memory you make, Every story you tell, every glance at the stars is part of the universe's great library. The fact that the library may one day fall silent only makes its present song more profound. Close your eyes and imagine a thought, a single thought floating in the darkness. Perhaps it is the memory of your childhood home, or the face of someone you love, or even just the sound of your own. Normally, thoughts are tied to a thinker. They arise from the living machinery of a brain, from neurons firing, from years of memory and experience. But in the far future of a dying universe, physicists have wondered, could a thought appear on its own, unanchored, a brief flicker of awareness assembled by chance from chaos? This is the strange idea of the Boltzmann brain. The name comes from Ludwig Boltzmann, a 19th century physicist who studied entropy and the probabilities of order arising from disorder. He suggested that if the universe were eternal, with infinite time to shuffle its particles, then improbable arrangements might occasionally form. Given enough time, the random motion of atoms could, in principle, assemble anything. A table, a tree, even a conscious brain. It would not last long. It might dissolve in a fraction of a second, but during that instant it might experience a thought, complete with memories that never truly happened. The idea sounds fantastical, like something from a dream or a fable, but it emerges directly from the mathematics of entropy. In a universe approaching heat death, where everything is spread evenly, the most likely state is featureless fog. Yet if the fog continues forever, it is not impossible for chance to build a temporary pattern. Just as wind might briefly sculpt a sand dune that resembles a face, or clouds might form shapes that look like animals. Over eternity, the improbable becomes inevitable. To picture this, think of shaking a jar filled with Scrabble tiles. Most of the time they will land in random piles, meaningless jumbles. But if you keep shaking the jar for long enough, there is a tiny chance they could fall into a word. Shake longer still, and perhaps they could spell a sentence. Shake long enough, and they might even spell an entire book. The odds are vanishingly small, but given infinite time, they are not zero. Boltzmann brains are like those sentences in the jar. Temporary arrangements of chaos that, for a moment, form something that looks like meaning. The paradox comes when you ask, if the universe lasts forever, wouldn't these fleeting, accidental minds eventually outnumber minds like ours? After all, it takes billions of years of cosmic evolution to produce life, planets, and brains that think slowly and steadily. It would take only a moment of chance to produce a Boltzmann brain. If eternity gives us infinite moments, then perhaps most thoughts in the universe are not the product of stars and life at all, but the random flickers of fog briefly imitating consciousness. For those lying in bed, this idea may sound unsettling, as though your own awareness could be a dream conjured out of nothing. But there is no need for alarm. The paradox is not meant to undermine reality, but to highlight the strangeness of infinity. It is a riddle, not a prophecy. In practice, we have no evidence that Boltzmann brains exist, and many physicists believe that a well-behaved cosmology should avoid producing them at all. They serve as a test of theories. If your model of the universe predicts a cosmos dominated by random hallucinations rather than real histories, perhaps the model is incomplete. Still, the imagery is haunting in a gentle way. Imagine the universe in its twilight, a fog of particles stretched thin. From time to time, chance stirs that fog into temporary shapes, a ripple that for a moment resembles a brain, complete with the illusion of memory. In that instant, it might feel as though it has lived a whole life, even though it has only just appeared. And then it dissolves again, like a dream vanishing the moment you wake. Perhaps the best metaphor is dreaming itself. When you dream, a story arises without your conscious control. Entire landscapes, conversations, even histories seem to appear from nowhere, coherent only while you are inside them. A Boltzmann brain is like a dream without a dreamer, a mind without a body, a memory without a past. It is fragile, fleeting and lonely, existing only long enough to realise its own strangeness before fading. The comfort in this idea, if there is one, lies in the reminder of how extraordinary real history is. You're not a flicker of fog. You're the product of stars forging elements, planets coalescing, life evolving across billions of years. Your thoughts are woven from the deep time of the cosmos, not from its random noise. Boltzmann brains are curiosities and equations. You are a story written in starlight. And yet, the paradox leaves us with something to ponder. If endings stretch long enough, if time runs into infinity, then even the most improbable events must occur. The question is not whether they can happen, but whether they matter. A brain that lasts for a fraction of a second and believes it has lived a life is not the same as a being who actually lives that life. One is a flicker, the other is a flame. The distinction reminds us that meaning lies not only in what is possible, but in what endures. So, as you drift towards sleep, think of Boltzmann brains not as threats to your reality, but as cosmic dreams, the universe imagining itself in rare and fleeting moments. They are whispers in the silence, curiosities of entropy, the smallest possible sparks of awareness against the backdrop of eternity. They may never matter in practice, but as an idea, they show us just how strange infinity can be, and how precious it is that you are here, now, in a universe still rich with real patterns, real stories, and real light. Imagine blowing a soap bubble. The surface glimmers with colour, swirling rainbows shifting as it floats through the air. Now imagine not just one bubble, but a whole cluster of them, each shimmering with its own hues, each bumping gently against the others. This image, delicate and playful, is one of the ways physicists describe the multiverse. A great froth of universes, each expanding on its own, each perhaps with its own rules, its own constants, its own story. Our universe would be just one bubble in this cosmic bath, one shimmer among countless others. The idea grows from a concept known as eternal inflation. In the early moments after the Big Bang, space did not expand at a steady pace. Instead, it inflated rapidly, faster than light could travel, stretching tiny quantum fluctuations into vast structures. That inflation eventually slowed in our region, allowing galaxies and stars to form. But in many models, inflation does not end everywhere at once. Some patches of space stop inflating and become universes like ours, while elsewhere inflation continues, budding off new bubbles endlessly. Each bubble is a universe, a region where inflation has paused, allowing matter, energy and structure to emerge. What makes this idea so haunting is not just its extravagance, but its subtle hints that we might detect traces of it. If universes are bubbles floating together, then sometimes they might collide. Just as soap bubbles leave faint scars where they press against each other, two cosmic bubbles brushing together could leave imprints in the light of our own universe. Some scientists have searched for such signs in the cosmic microwave background, the faint afterglow of the Big Bang. They look for unusual circular patterns, cold spots, or ripples that might betray a neighbouring universe brushing against ours long ago. The evidence so far is inconclusive. There are hints, whispers, anomalies that spark debates, like the mysterious cold spot in the southern hemisphere of the microwave sky. Some suggest it could be the fingerprint of a collision with another bubble. Others say it is simply a statistical oddity, a patch of sky colder than average by chance. In science, caution reigns. But the possibility lingers, like the memory of a shadow glimpsed at the corner of your eye. To make the concept more tangible, think of lying in bed with your eyes closed and hearing muffled music through the wall from another room. You cannot see the musicians, you cannot join the party. But the faint rhythm, the vibration through the wall, tells you that something is happening beyond your immediate space. The search for multiverse hints is like listening for that distant music, looking for faint signals that suggest we're not alone. that our bubble is not the only one floating in the dark. The thought is both humbling and comforting. Humbling, because it reminds us that our entire observable universe, with its trillions of galaxies, might be only a tiny patch in a much greater expanse. Comforting, because it means endings here might not be endings everywhere. If our bubble fades, others may continue. If our physics dissolves, others may thrive. The multiverse turns the loneliness of cosmic death into the possibility of endless company, though company we can never reach. Of course, one must be careful not to mistake imagination for certainty. The multiverse remains speculative. It is born from equations that describe inflation, but equations are not proof. Still, its poetry is undeniable. To think of countless universes, each glowing with its own rules, each drifting beside ours, is to enlarge the stage of existence beyond anything we can see. It turns our universe from the whole story into one chapter in a much larger book. Perhaps the greatest gift of the multiverse idea is perspective. Imagine once more the soap bubbles floating together to the creature living inside one bubble. The surface is infinite. The bubble is everything. Only by stepping back could you see that it is one among many. We too live within our bubble, unable to step outside. But to consider that there might be others is to glimpse beyond our horizon, to let the imagination drift where our senses cannot follow. For a listener at night, this thought can be oddly soothing. Your world is vast enough to hold oceans and continents, skies and stars. The universe is vaster still with its galaxies and clusters, but the multiverse stretches the canvas even further into possibilities we cannot exhaust. It says, "What you see is grand, but it may only be a beginning." The song may have many verses even if we only hear one. So when you hear the phrase eternal inflation or bubble universes, do not think only of complex mathematics. Think of children blowing soap bubbles on a summer afternoon, each drifting upward, fragile, beautiful and fleeting. Each one shines for a moment and then drifts away. Our universe is such a bubble, shimmering, temporary and luminous. And if the multiverse is real, then somewhere, right now, other bubbles are forming, other lights are glimmering, carrying stories we will never read, but that nonetheless exist in the quiet froth of infinity. If you have ever stood in front of a mirror and looked at your reflection, you may have wondered whether the person on the other side is somehow real. They move as you move, they smile as you smile, but they live in a space you cannot reach. This simple act, seeing another world that resembles yours but remains untouchable, is a small metaphor for how some physicists think of the multiverse. Our universe may be one reflection in a hall of infinite mirrors, one world among many, each shimmering with its own laws of physics, each carrying stories we will never step into. The idea is not merely fanciful, it grows out of puzzles at the edge of physics. Eternal inflation suggests an endless froth of universes, but quantum mechanics and string theory offer their own versions. In the quantum picture, every possibility is realized, every branch of probability unfurls into a separate world. In the string theory landscape, the equations that describe fundamental particles allow for a vast number of possible configurations, each one corresponding to a different universe with different constants. To us, these are abstractions, but the implication is clear. Our universe may not be unique. It may be part of a greater sea of realities, each with its own flavour. Within this picture, some physicists have asked, if the end is inevitable here, might there be escape elsewhere? Could the death of one universe be the birth of another, or the doorway to another bubble? In some speculative models, when vacuums decay or bubbles form, they can spawn new regions of space with fresh physics. Perhaps information is not lost but carried forward, encoded in the transition like seeds drifting on the wind. Perhaps the cosmos is less like a single life with a single ending and more like a great tree, branching endlessly, each twig a universe, each leaf a story that will one day fall, but the tree itself enduring. The holographic principle adds another layer of reflection. According to this idea, everything that happens inside a region of space may be encoded, like a hologram on its boundary. Imagine a snow globe. The world inside seems three-dimensional, with houses and trees and swirling flakes. But in principle, every detail could be stored on the surface of the globe, like an intricate engraving. In a similar way, some physicists suggest that the information of our universe may not be lost even if the interior dissolves. It may be preserved at the edges, written in a code we cannot yet read. In that sense, even the fading of matter and energy might not mean the fading of memory. This is not proof that rebirth awaits us, nor that information is guaranteed to survive. It is instead a gentle reminder that the cosmos may hold more layers than we see. What feels like an ending may be only a transition, a change of stage. One bubble dissolves, another forms. One branch fades, another grows. The tapestry may be far larger than the single thread we follow. To make this thought easier, consider the tide at the shore. You watch the waves retreat and it feels like loss. The sand grows bare, the water slips away. But then, without fanfare, another wave returns, reshaping the beach, carrying shells and driftwood to new places. To the sand, each retreat might feel final, but to the ocean, it is only rhythm. The multiverse invites us to think of universes themselves as tides, each retreat and return part of a larger pattern. Or think of sleep itself. Each night you let go of the day, your mind quiets, your awareness fades. To the wakened self, this is an ending. And yet, within that ending, dreams arise. Stories unfold in the darkness, worlds built from fragments of memory. In the morning you return, renewed. If consciousness can carry endings within itself and turn them into beginnings, perhaps the universe can too. Perhaps endings are not empty, but pregnant with the seeds of other stories. These reflections are not meant as answers, but as invitations. We do not know if other universes exist, nor whether they touch ours, nor whether endings here are beginnings elsewhere. But by thinking of them, we are reminded of the scale of possibility. Our universe is vast enough to hold galaxies and black holes, stars and life, yet it may be only one chapter in a library so enormous that its shelves stretch beyond imagination. The multiverse is that library. We cannot wander its halls, but we can imagine their existence, and in doing so we remember that our own story is precious, even if it is one of many. So when you hear that the universe may end, you can also think that it may continue. In another bubble, another mirror, another leaf on the tree of reality. Whether or not we ever glimpse those other worlds, the thought itself is a comfort. It tells us that endings need not be absolute. They can be doorways, reflections, rhythms, part of a pattern too large for us to see. And in that sense, the cosmos, like a lullaby, does not stop with a single note. It continues softly, in harmonies beyond hearing, in verses beyond our page. If you have ever stood on a shoreline, you know the rhythm of the sea. A wave rushes in, foaming at your feet, then retreats, drawing sand back into the water. For a moment the beach seems quiet, emptied, and then another wave arrives, reshaping the shore again. To us this is natural. The ocean does not stop with one tide. It moves in cycles, retreating and returning, breathing in and out. Some physicists have wondered if the universe itself might behave in a similar way. Instead of ending in silence, perhaps it expands and contracts in cycles, each ending a new beginning, each retreat a preparation for return. This idea is sometimes called the Big Bounce, a cousin to the Big Crunch, but with a twist of renewal. In the crunch, the universe collapses under its own gravity into a hot singularity, a final implosion. In the bounce, that collapse is not the end, but a rebirth. Just as a compressed spring can snap outward again, a contracting universe might trigger the birth of a new expansion, A new cosmos, a new story unfolding from the ashes of the old. The appeal of this idea is obvious. It rescues the universe from finality, turning death into rhythm. It suggests that instead of a single arc from beginning to end, reality might be an eternal circle, endlessly reinventing itself. Some ancient cultures, long before modern physics, imagined the cosmos in cycles. Worlds created, worlds destroyed, worlds reborn. The bounce gives that intuition a scientific echo. Different versions of the theory describe different mechanisms. In some models, the collapse squeezes matter and energy so tightly that quantum effects push back, halting the singularity and sparking a new expansion. In others, inspired by string theory, our universe is like a three-dimensional sheet, or brain, floating in a higher dimensional space. Collisions between brains could cause repeated bursts of creation, each one a new Big Bang, each one a new universe blossoming from the impact. Roger Penrose has suggested yet another possibility: conformal cyclic cosmology, where the far future of one universe, stretched so thin by expansion that particles lose their mass, can be mathematically rescaled into the beginning of the next. In this vision, the universe is a chain of epochs, each fading seamlessly into the next, like pearls strung along an infinite thread. To imagine these cycles is to imagine the cosmos with the patience of tides. Our entire observable history, stars, galaxies, life, humanity, would be just one small crest of the wave. Beyond us lies an endless sequence of other crests, other stories, other universes, each rising and falling in turn. The grand scale is difficult to picture, but the rhythm is simple, familiar, like breathing. And yet, the evidence for cycles remains elusive. The universe we observe seems to be expanding faster and faster, not slowing toward collapse. The fingerprints of the cosmic microwave background suggest a beginning in a hot, dense state, but they do not clearly reveal what came before. A few anomalies, such as unusual circular patterns in the background radiation, have been suggested as echoes from a previous cycle, but they remain debated. At present, cycles remain an elegant possibility, not a proven path. Even so, the thought has its own gentle comfort. A universe that ends in silence feels final, absolute. A universe that bounces feels less like a death and more like a pause, a chance to begin again. To imagine that everything you see, the stars, the galaxies, even yourself might be part of a rhythm that is repeated countless times, is to feel small, yes, but also connected to something endless. You're not on a straight line headed for stillness, but on a tide that flows forever. There is another perspective too. Even if the cycles are only imagination, the metaphor itself is valuable. Cycles remind us that endings can contain beginnings, that silence can carry the seed of sound. Think of sleep itself. Each night you let go of the day, sink into darkness, and in the morning you return, renewed. To the day, sleep is an ending. To the larger rhythm of life, it is a necessary return. If the universe sleeps and wakes in cycles, then its rest is not loss, but renewal. The beauty of the bounce lies not in certainty, but in possibility. We do not know whether the cosmos truly breathes this way, but to imagine it is to soften the sting of finality, to see death as part of a greater rhythm. Whether or not the evidence ever proves it, the thought itself is a lullaby, that no ending is final, that each retreat may carry within it the promise of return, that the sea of existence never truly falls silent. And so we reach the end, not only of tonight's story, but of the story of everything. Across the last sessions we've walked through eras filled with stars and silence, fire and fog, collapse and rebirth. We have imagined cities of galaxies growing quiet, black holes shimmering away in whispers of heat, and even the strange possibilities of universes beyond our own. Now, as the journey closes, it is time to let the cosmos rest. The truth is, we do not know exactly how the universe will end. It may freeze into stillness, rip itself apart, collapse into a final blaze, or transform into something unrecognizable. It may bounce into a new beginning, or dissolve into the quiet fog of entropy. But however it happens, one thing is certain. The universe is not rushing. Its endings are written in spans so vast that they make even galaxies seem young. To think about them is not to predict our own future, but to meditate on patience itself. Perhaps the best way to picture the universe's end is not as a catastrophe, but as a kind of sleep. Every day you live follows this rhythm, brightness, activity, sound, and then night arrives. Your body grows heavy, your mind slows, your eyes close. The world does not vanish, but it recedes, softening into stillness. You fall asleep not with fear, but with trust that rest is part of life. The cosmos too may one day fall asleep, not with a crash, but with a long sigh, a gentle drifting into rest. This image can soothe us, because it transforms cosmic endings into something familiar. Think of a candle burning low, its flame shrinking until only smoke remains. Think of an old song fading into silence, the last note lingering in the air before dissolving. Think of snow covering a landscape, softening its details, leaving only white. Each of these is an ending, yes, but each carries with it a certain piece. None of them erase what came before, they complete it. And in that completion lies meaning. For what gives a story its shape is not only the beginning, but the end. The universe's story, like all stories, is precious because it has a rhythm. To live within it is to dwell in a fleeting but luminous chapter, filled with light, warmth, and memory. Whether or not there is another chapter beyond, this one is already a wonder. There is also a quiet comfort in the idea that we are part of this unfolding. You're made of stardust, the carbon, oxygen, and iron in your body, forged in the hearts of stars long gone. You carry the memory of the universe's brilliance in every breath you take. To imagine the cosmos resting one day is not to imagine something separate from you. It is to imagine the source of your being, the cradle of your elements, finding its own peace. And maybe, just maybe, endings are not as final as they seem. Perhaps in another bubble of the multiverse, another story is already beginning. Perhaps when one cycle closes, another opens. Or perhaps the universe's true gift is not in what comes after, but in what it already gave. The chance to exist, to wonder, to dream under the stars while they still shine. So as we close tonight, let us think of the universe not as dying, but as resting. It has lived a long and luminous life. It has given us galaxies, oceans, sunsets, laughter, and questions without end. One day it may close its eyes, folding into silence. But even then the silence will be filled with memory, like a lullaby echoing in the dark. And so, dear listener, whether your own eyes are still open or already drifting shut, thank you for walking with me through this story. If your thoughts wander now, let them. If you drift into sleep, let it take you. The universe itself may one day do the same, and in that stillness there is no fear, only peace, only rest, only the quiet hum of a cosmos that has finally settled after its long, brilliant day. Good night. Sleep peacefully wherever and whenever you may be.